Hello, my name is Leonardo Villalobos. I'm a student at the University of Costa Rica, and today I'd like to present to you our research paper titled Evaluating Hyperparameter Tuning Using Random Search in Support Vector Machines for Software Effort Estimation. Many years before and up to date, machine learning has been used to create accurate software effort estimation, or SEE, models, and particularly support vector regressions, or SVRs, have been proven to be an effective technique for SEE because these models offer certain flexibility or adaptability to different types of data. However, this adaptability and thus their performance depends on the correct selection of hyperparameter values. Because of this, many studies that have employed SVRs have also employed grid search hyperparameter tuning to exhaustively select these hyperparameter values. However, an alternative called random search has been proposed that can achieve similar results using a lesser amount of computational resources. Because of this, we propose the main objective of our study to investigate what is the extent that the random search hyperparameter tuning approach affects the accuracy and stability of SVR in SEE. To meet this objective, we ask the following three research questions, which are: what is the improvement in prediction accuracy of SVR when random search is used? What is the prediction stability of SVR when random search is used? And which of the models evaluated in this study yield the best accuracy for SEE? I present to you now the design of this study, starting with the dataset. And we have selected the ISBSG 2018 Release 1 dataset, which consists of around 8,200 projects and 250 features. Because this data comes from different organizations around the world, it has several problems such as heterogeneous data, as well as many missing values. Because of this, the ISBSG, as well as the literature, recommends to perform some pre-processing to the dataset before using. In our case, we have selected to first partition the data depending on the functional size of the development projects. In this case, we have selected two functional approaches, which are Cosmic and ifbook4 plus. Moreover, for each functional size, we have created two datasets, which are the one using the function point total and another using the basic function components only. For each of these datasets, we have selected only those projects that are high quality, A or B, according to ISBSG, are new development projects, and the recorded effort accounts only for the development team. For features, we have selected only those features that are relevant for SEE based on the literature, and we have removed features with more than 25% missing values. The four resulting datasets, as well as their amount of projects and features, is shown in the table on the right. For the machine learning algorithms studied, we have selected four types of algorithms, starting with data transformation, for which we have used node transformation and the logarithmic transformation. For feature selection, which have used no feature selection based on variance thresholding, and feature selection that selects the top percentage of features correlated with the target feature. For learning algorithms, we have selected the SVR as well as a regression method as a base for comparison. In this case, we have chosen ridge regression. One important detail is for SVR, we have chosen to not use a feature selection approach because on preliminary executions of this study, we have found that they had almost no effect on the accuracy. Lastly, for parameter tuning, we used three techniques: random search using 60 samples, grid search, and default parameters as a baseline. Thus, by combining all of these four types of techniques and accounting for the fact that SVR used no feature selection, we have evaluated 24 different models in this study. And we will use the following type of abbreviation to refer to them throughout the study. So for example, if we select for DT, we select log. For feature selection, we select none. For LA, we select SVR. And for tuning, we select random search. The abbreviation would be RS plus log plus SVR, and so on and so forth. For hyperparameter values, we have used the values shown on this table. These values were selected based on recommendations and previous studies on the literature, as well as preliminary executions we performed on the dataset. For SVR, we evaluate around 4,100 parameters, and for the 3 different ridge regression models, we evaluate less than 300 values. Other configurations of the study include: we use 10% of the total data for each dataset as a test set to validate the results of the study and discard problems such as overfitting and data mismatch. For cross-validation, we use 10 times 10-fold CV. In addition, each tuning approach uses an inner CV. In this case, we have selected 10-fold CV. For missing values, we have selected the nearest neighbor technique. To transform the categorical features of the dataset, we have used the one-hot encoding approach. And finally, for calculating the standardized accuracy metric, we use the baseline model proposed by Landon and others. For metrics, we use those recommended in the literature based on the absolute residual or absolute error. In this case, we use the median absolute residual, as well as the standardized accuracy and its effect size. To calculate the accuracy and to evaluate the stability, we use the standard deviation of the absolute residual. For improvement, or based on the recommendations of Tanti Thaborn and others, we use 2 more metrics, which are the improvement ratio and the stability ratio. In these cases, they both measure the increase in stability or accuracy for a tuned model against an untuned model. I will present now the results of the study, starting with the first research question: how does random search improve the accuracy? In this case, for all in the 4 data sets, random search improved the most the accuracy with respect to default parameters in 2 techniques, which are log plus SVR and SVR. In the case of rich models, we can see that there is some improvement in the majority of cases. However, this improvement is smaller than that achieved with SVR models. Going more in detail of tuned versus untuned models, we can see here for each of the datasets that there is a similar pattern. For example, if we take the IFBook4 plus UFP, we can see that the untuned SVR achieves around 26% standardized accuracy. However, when we apply parameter tuning, we can see that the SA can reach around 42%. And in this case, we also can see that the difference between random search and grid search is relatively small, less than around 2% standardized accuracy. We can observe this behavior using node transformation or log transformation, as well as in all 4 datasets. With this, we can observe that not only random search improves the accuracy of SVR compared with default parameters, but also it functions similarly or achieves similar results than grid search. To answer the second research question, we present here the stability ratio. It is interpreted in the inverse way than standardized accuracy, meaning a lower ratio is a more stable model. And again, we can observe that the 2 models that are most impacted by random search, thus becoming more stable, are SVR and log SVR. However, the stability achieved is around, or the ratio achieved is around 0.8 to 0.9. In the case of rich models, we can see that in the majority of cases, the ratio is around 1, which means that the stability is maintained. Going more in detail of tuned models against untuned models, we can observe that, for example, for ifbook4 plus UFP, an untuned SVR has a standard deviation of the absolute residual of 9900, but when we use tuning, it is reduced to 8500. And again, we can observe that the difference between random search and grid search is relatively small. This holds true when we use or not the logarithm transformation, as well as when we for all 4 datasets. And again, we can observe that not only does random search improve the stability by reducing the deviation, but also we can see that random search and grid search behave similarly and achieve similar results. To answer the third research question of which techniques are the most accurate in SEE, we used a Scott-Knott analysis based on the standardized accuracy of all evaluated models for each dataset. Starting with the Cosmic BFC dataset, we can see that the top cluster consists of tuned SVR models using or not using the log transformation. The second group consists of untuned SVR models, and the third and fourth groups consist of rich regression models. For the Cosmic FFP dataset, we can see that the first group is tuned log SVR models, the second group tuned SVR models, and the third group is a combination of SVR and some of the tuned rich regression models. The remaining groups are consisted of the remaining rich regression. For ifbook BFC, we can again see that the top group is tuned log SVR, the second group is tuned SVR, and the third group is untuned SVR. The remaining groups are again rich regression. And finally, for the ifbook UFP dataset, we can observe again the first, second, and third groups are exactly the same as before, and the fourth group onwards are combinations of different rich regression models. Based on this, we can observe several patterns. The first one being, in all cases, SVR either ranked equally or above rich regression models, where the SVR models tuned or not. The second one was that for SVR, parameter tuning plus SVR always ranked above using no tuning with SVR. And third, we could observe also that the top group or the top cluster consists always of hyperparameter tuning plus logarithm plus SVR. To present the results or the conclusions of the study, we could determine that hyperparameter tuning improves accuracy and stability, and moreover, that random search and grid search provided similar improvements to accuracy and stability. Regarding the best models, we determined that hyperparameter tuning, logarithm, and SVR are ranked above the other models evaluated in this study. And in addition, we compared the results we obtained in this study with previous studies in the literature, including Ertugrul and others, Song and others, and Hosni and others, obtaining results that are in line with previously reported results. For future work, we want to extend this study to cover a wider range of hyperparameter techniques, machine learning algorithms, datasets, primarily those of the PROMISE data repository, and other methods to lower computational cost. We would also like to study how does the amount of search parameters, which was 60 in this study, affects the increase in accuracy that random search can provide. And finally, we would like also to study the properties of the ISBSG 2018 dataset and determine which preprocessing would have helped increasing accuracy. I would like to thank you very much for your time and attention. And if you have any questions or comments, I'll be glad to hear them. Thank you very much.